Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video is going to take a look at everyone's most mind-bending, most favorite topic when it comes to computer programming and computer science, recursion. So have you ever Googled recursion? The definition of recursion, their definition is the repeated application of a recursive procedure or definition. And so did I mean recursion when I Google searched for recursion? Of course I did. And you can imagine I could do this all day long and laugh my butt off the entire time, 6,000 times through, because I'm just calling myself and calling myself over and over and over again. What a subtle joke, right? Hilarious. So what is a recursive function? At its simplest, from when it comes to computer science here, the definition is just a function that calls itself. Because we have, main calls functions, and the functions we create call other functions, and so forth and so on. Object-oriented programming, member function calls functions and member functions, and so forth and so on. It's just a little bit different. I mean, to the computer, it's no different than anything else, but to us, it's that mind-bending, like what the heck is going on, because the function is calling itself. So I just stole this blast-off function, and we're taking a look at that here. So what am I doing here? Let me just run this program, just drag this over here. Don't kill the disassembly. And so you can see it prints 20, 19, 18, 17, 16, 15 down to 1, and then it prints blast off. And you go, well, what is it doing? How is it doing it? And so countdown of 20 calls. That's what I'm calling here, and it calls this function. I can kind of, let me bring this down to 2, just so we can kind of make this a little easier to understand. Oh, let me put a breakpoint in there too. And put a breakpoint and run this one more time. And they go, what am I doing? F11 to go in. And I go, well, countdown. Num is 2 at the current moment. I passed a 2 in. I say, well, is num 2? And you go, or I'm sorry, is num equals 0? And you go, nope. So the else part is print the 2, and then look at that, call myself over again, but now num minus 1. So call that with a 1 instead. So I'll go into it, and now num is 1. It's not 0, so it's going to print the 1. Let me do this over here. Okay, so there it is. There's my 2, there's my 1, and now I can go in one more time. Whoop. I learned something there. F11 here. F11 full screens that. F11 is a step into in Visual Studio. So now num is 0. So then it'll print the blast off. And there's no more recursion because it falls through the else case. And so it returns back. And so now the hard part with recursion, of course, is understanding now I'm at this statement of code, but I'm at the second call. This is where just describing it is just bloody difficult. So I quit out of that and I come back and I go, nope, now I'm down to the first call of the function, the one with the 2. Num is now 2. So they say I've dealt with the 0 case, the 1 case, and the 2 case, and now when I hit F10 and I come out, now I'm actually done with this function. I can do my system pause, and I'm ready to go off and do whatever else. So it's, I say, I did not understand recursion as well as I should have when I was going through my undergrad. So if it's something that just doesn't come to you, there's only a few true cases we ever use recursion, like linked lists. I'm not linked lists. Yeah, linked lists sometimes, but sets and maps, those kind of things are definitely where we would use recursion. So we just kind of showed, I just kind of showed visually here in Visual Studio what this is describing when it comes down to the countdown function, how we stepped through all the code and just kind of made everything work. So I mean, we don't really need to talk about that any more than we already see. So solving problems with recursion, you go, well, okay, so what really happens, as we showed here, we started with countdown of 2, and then we reduced it to countdown of 1, and then countdown of 0. So it's like we did take a large problem and break it down into smaller and smaller chunks until we found a chunk that we could actually solve, and then we let the magic of our call stack and the magic of just functions folding back upon each other, itself over and over and over again to figure out what the actual true solution to the problem was. So to get out of this thing, because this would never be an infinite loop, this would be what we call a stack overflow. Because if this num1 case, because if I just get rid of this thing, just get rid of the if statements and just run it, I will, and I hit F5 to run through, and you go, yep, okay, first off, you'll see this over here. You go, blah, 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 blast off, blast off, blast off. But you will, oops, where is, oh my, what is happening there? Hold on. Oh no, what did I just do? But there's the exception that's unhandled. It's hard working with 2 screens when both screens look exactly the same. So, and I have a stack overflow because my memory, the memory for my stack, there's only so much of it. And so if I'm infinite looping it, like I said, countdown, 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 eventually, no matter how much memory I have, eventually I would run out of space. So let me undo, undo, undo. So the recursive calls will stop when the base case is reached. In this case, it's num equals 0, but otherwise it continues on. And say if you forget or you mess up and something goes wrong along the way, you have yourself a stack overflow. So in our case, num is 0. So I said we must always have that, or we end up with that stack overflow. So I'm just repeating that here. So again, the num equals 0, that is that, and then this is everything else that runs normally if that base case is not met. So eventually the parameter, yeah. So it's these are just iterations of the same information. So start with a number and work your way down to something that can actually break the chain, and then when you break the chain, it'll break its way back all the way. So then, yep, there's that. So, but the thing is, like, what is actually happening? And if you're taking the assembly language class, or will be taking our assembly language class, this is chapter 8 kind of stuff. And so every time I call any function, what I'm doing is I'm putting a memory address on the stack for where to come back to when that function is done. And then I'm also, for every parameter I'm also passing that information onto the stack as well. That's why I'm just like, why does this stack overflow? It's because every time I call a function, even if I don't pass a parameter on, I'm always putting something on it, which is a memory address from where to return to. So then a new copy, and I say every time around, the new copy is called, and then every time around, we call this an activation record. And so what happens is at this function call at this moment in time, that num variable applies to me. But if I recurse, that function has a new num variable that applies to it, and so forth and so on. And so every time a function executes and returns back, all of that stuff is popped off the stack. All the parameters and then that memory address, and we return back to wherever it came, because how else will the computer know where to return to unless we stored that information somewhere? And eventually we make it back to the initial call, say we call, or call, and then hit the base case, return, and then eventually now we come back and we're finally done recursing, the function is done, and now we're back into normal land here. We're doing the same stuff we always did. So I say according to this, there are 2 ways of doing this, direct or indirect. I don't feel like I need to discuss indirect because I've never seen it in all my years. Everything I've always done is direct. If you know of an example, I'd love to see it. So just send me a comment or send me an example if you know of something that actually uses indirect recursion. Usually recursive functions are simple. They're small enough so that you don't need to have multiple functions going on, but prove me wrong. I don't know. I do not know. So another one of these functions that works is the factorial case. So factorial, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2, that kind of thing. And I could create a function, int factorial, and I pass int in, int out. So usually I just use an n here. And then I can say my base case, if my n value is less than or equal to 1, I will return 1. And this just handles what happens because 0 factorial is 1. I just can find a number file video if you're interested in that. 1 factorial is 1, and then everything else is 2, and then 6, 24, 120, 720, and so forth. And so what do I do with negative value? I don't think there is such thing as a negative factorial. I'm sure some mathematician did somewhere. But in this case, I don't necessarily care. So if n is less than or equal to 1, return 1. Otherwise, return n times factorial of n minus 1. And so, just like before, as long as I start with a number above 0, or in this case above 1, then it will recursively call over and over and over again. And so in this case, again, we're talking about this call stack, we're multiplying numbers together, 1 times 2 times 3 times 4 times 5. So before any stack overflow would ever occur, we would have an overflow, because an int, 32-bit integer, can only hold values up to 4 billion, and I believe we can only go up to like 18, 17, 18, 19 factorial before this becomes a problem. We can find out. For int I equals 1, or you can even, if you want, I equals 0, I is less than or equal to 24 plus I, and then I could do a cout. whatever that was, for factorial of I, and then do an inline. Okay, and then see what we get. Oops, gotta get rid of this. There we go. So 1, 1, 2, 6, blah, 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 blah. And so I guess, you know, because there's going to be zeros after a while. So this one right here, wherever this one is, 1, 2, 3, 4. Here, let's just, instead of me counting it out, how about I just put something like that? And then now I can see it. There we go. So it is at 12 factorial. 12 factorial is the largest one we can represent. Or maybe that's not even, yeah, 11 times 12. Yeah, looks like 12 factorial is the largest number that we can represent because it overflows immediately. And Python can handle it just fine because Python actually, because it's such a dynamic typed language, it can actually grow to expand to settle that for us. That's pretty cool. So this is all I did, right? So the base case for this fact is this figuring out, you know, if I'm going to keep subtracting. And so once I finally get to a number that, you know, a small enough number, then I can return 1. That's the whole idea here. And let's see, I did the code a little different. I mean, it's basically the same kind of stuff. I just kind of reversed the loop. If, you know, and this is probably a little better. If number is greater than 0, do this, which is this here. Otherwise, return 1, because this is only going to happen one time, but this is going to happen over and over and over again. And just from an efficiency standpoint, that extra jump is going to slow me down. So whatever, who cares, right? So then here is basically the same function. If n is equal to 0, return 1. You know, so like, what do you do with a negative? Ooh, but -1 would probably go crazy, right? Like, what would happen if I just say, if n equals 0, return 1. Otherwise, return n times factorial of n minus 1, and then just put a -1 in here. Let's just see, let's get rid of the for loop altogether, and let's just say print out factorial of -1. Oops, almost there. Stack Overflow, because all we were checking was against n is equal to 0, and so it would say, okay, return -1 times factorial of -1, which is -2, and so it would keep on going. It would never hit. My only question is, what is the n value? -4,789 is when this thing crashes. That's interesting to you. That's interesting to me. All right, whatever. So other functions, greatest common divisor function. So this one is like, what's the largest factor that two integers have in common? So Euclid, way back in Euclid's day, thousands of years ago, figured this one out. And this one is, you know, it's one of those, again, it's when a lot of times recursive functions, they turn out, you know, they're very simple when it comes to the number of lines of code, but the problem comes from understanding what the heck that code does. So if I say return, just to throw this out here, just to make this a one-liner and feel awesome about this, I could just be like, okay, return x mod y equals 0, return y, otherwise return GCD of y, comma x mod y. So this is just using the ternary operator and just kind of reducing this. Move this over just a little bit there. So yep, so there we go. And pick any two numbers. I don't have anything off the top of my head. 115. I think this should give us 5, right? It does, because 5 is the largest number that goes into both 100 and 15 evenly. So 5, yep, so there's no 6 or no 7, 5, and 5 goes into both. So yep, that sounds about right. And what happens is pick random numbers. So I pick a prime number. It's 115 prime. Yeah, 115. I guess 115 is prime. There's 2, so that's it, right? So just 2 is the greatest common divisor. But it's the same deal, and again, I'm not going to get into the algorithms per se, because you can look up Euclid's algorithm, how it actually works if you so choose. But it's just saying that the base case ends up being, if the mod of these two numbers ends up being 0, then I finally eliminate the idea of the recursiveness, and I start falling back on myself. And so that's the idea, and that's one-liner versus a couple liners. That's all we need to do. So let's see, what else have we got? Fibonacci. You know, Fibonacci starts with a 0 for the first value, a 1 for the second, and then everything else is just the summation of the two previous values. And we can get into discussions about, let's see, do they count 0? Let's see, number 0 is 0. Okay, so just to say the 0th number in the Fibonacci sequence is 0. So I say, which number do you want? If n is equal to 0, I will return 0. If n is equal to 1, I will return 1, because these are our base cases. Otherwise, I will return Fibonacci of the previous two numbers from the nth number, n minus 1 plus Fibonacci of n minus 2. And so, so it should, well, here are the numbers here on the screen, point over there, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, so forth and so on. So we can now just quickly just jam in another for loop for int I equals 0, I is less than, we'll do the first 20, this, that, whatever, and just say print me Fibonacci of I. And I don't need a end line this time. I'll just put a space between them. So 0, 1, 1, 2, 3, 5, just like before, right? Just looking at the numbers up to 21, and then here we go, and it just starts growing pretty much, quickly because it's the sum of the previous two numbers. So that's, I mean, how would there's a lot more to this if you were going to do this what we call iteratively and not recursive. That's something we haven't really discussed here, is like, how would you do a factorial? How would you do this countdown? How would you do Fibonacci if you didn't have access to recursiveness? And so in these cases, some of these, since I've done, I mean, maybe just because I've done them enough times over the years, they're easy to me, and just I understand what's happening. But like with the Tower of Hanoi problem, which we'll see here in a little bit, it doesn't matter. Doesn't matter how you discuss it. It's just mentally, just gets on you mentally trying to figure out what to do. So this is pretty much exactly what you see here, and what I did versus what they did. So there you go there. And so other things we can do, recursive linked list operations. I already got an email today from a student asking about that, and they say, well, I can, because I can recursively go through an algorithm. Like if I want to know the size of, I want to know the size of the linked list, I have to physically go through and count 1 by 1 by 1 by 1 by 1 to see how many elements are there. But what I can do is just say, okay, if I start with the head pointer and say, hey, are you null? And you go, nope. If you're not null, then I could say, oh, at least there's 1, and then I can pass along the next pointer to the same function and just keep asking that question. And so every time I find that it's not null, I add 1 plus I send off and try again with the next pointer. And eventually when we come up to the null pointer, I return a 0, and then basically everything returns back of 0 plus 1 plus 1 plus 1, plus 1 plus 1, until finally I come back, and there is the size and number of elements. And so so that's what we're discussing here in the slide I just discussed. Start at the head of the list. If it's a null, return 0, else return 1 plus the number of nodes. So I'm not going to write this out here. So one thing you notice here is normally these functions are pretty simple here, int n, countdown, int n, but like this can get a little daunting, especially with more complicated data structures. Like what is I'm going to pass a list node pointer to this thing, and I go, nope, because this is something that would happen basically under the hood. This would be in an object that someone created, and it would be sitting under the hood, so you cannot directly access the real function doing the work. And what I'm saying here is, generally speaking, there are two different functions that get generated that you create when you do this sort of thing. You create the public-facing function that is easy for the the end user to understand. So like in this case, I say, like, just give me the number of nodes. That's it. Give me num nodes or size. And so with no parameters, and it will return an inst, or an inst. It will return an int, and you're like, okay, that's something we can deal with, because I don't have to think about what's going on. But what happens then is, inside of this function is where I, as the developer of the class of the of the structure, figure out what the true recursive nature of this thing is. So the public-facing function almost always then we'll call the private-facing function. This is generally a private function, and so it'll say, hey, start with head and tell me how many nodes. And so the head will say, hey, are you null? Nope. Okay, return 1 plus tell me what happens afterwards. And so just like we're discussing, when we finally hit a null, we'll return 0, but then it'll be like 1 plus 0, then 0 plus 1, and 1 plus 2, 2 plus 1, you know, whatever it is, and we'll eventually get to the size when it returns back. Okay, so contents of a list in reverse order. So like, this isn't reversing the list, this is getting the contents of the list in reverse order. So other ways to do this is to just have a stack. You know, put all the information, go through the data structure one at a time, put it in the stack, and then pop. You know, push, and then pop, pop. But in this case, the algorithm says, let's start at the head of the list. If the pointer is null, then return. Don't do anything, because if I'm going through and you go, okay, null, but otherwise, if it's not null, first advance to the next node, say go to the next node, but when you come back, then print yourself. So if you do it, it depends, you know, the order of the two operations determines if the thing is, if we print in order or in reverse order. So like, if I can I steal this? No, that's not code. So no, I don't have list pointers or anything anyway. So I say I have my front-facing, my public-facing function that says display backwards, and it calls the recursive private-facing function that does all the actual work. And so in this case, again, I pass head in, so I say start from the head, and I say, okay, you're not null. So I say now recurse, so recurse, and eventually we'll hit the null pointer. So we'll fall through, and then that stops the stack, because basically we're creating, like I was discussing, a stack. We could push information onto a stack, but we already actually, without even thinking about it, we have been creating a stack of information in the call stack. And so everything is actually in reverse order on the stack, even though we didn't even think about it. So as we come back out of these, you know, we fall out of here and we fall back, we come back to this line of code, because that's where, you know, this is where the recursion, and then I print the value. And because I go call, I'm at the second or the last node, so I'll print the last node's value, fall through, and then it comes back to here one more time, and then it'll print the second to last value. It prints everything in reverse order. It really does. And so what I was saying here is, this will do everything in reverse order, but if all you have to do is swap line 191 and line 192, and you will show in the correct order, because you'll hit a node and you'll print it, and then you go to the next node. You'll hit a node, you'll print it, then you go to the next node. So it will print, instead of, you know, 5, 4, 3, 2, 1, it'll print 1, 2, 3, 4, 5. So, and of course the name of the function wouldn't be show reverse anymore, it would be just show forward, or whatever you want to think about it. So it's just, we're going to see this next time as well when we're talking about sets, and you know, when it comes to the binary search trees and things like that, binary trees, and just to see that the order of the operations matter, in order, pre-order, post-order, traversals, that kind of stuff. Okay, so this one, the Tower of Hanoi. I do not, I mean, I know how to do it, I get it, but I don't necessarily get it. So it's one of those, like, if I had my office, I have all the pegs sitting in my office, and it's coronavirus, so I hope everyone's doing okay out there, but I do not have this kind of stuff to show this. All my kids' stuff is, I took it to my office because I could use this. So the Tower of Hanoi is a mathematical game that is used to demonstrate the power of recursion. It just melted me when I was 19 years old. So the game uses 3 pegs and a set of disks, and you start everybody, hide, you know, like low, you know, like you see this at the biggest ones on the bottom, the little smallest ones on the top. There's 3 pegs, and the object is to move all the pegs from, just pick, you know, whatever one they're on, to something else. And you know, and so, I mean, like, how hard is that? Just pick them all up and put them there. And you go, yeah, that would be real easy. But the rules are, you can only move 1 disk at a time. You cannot put a bigger disk on top of a smaller disk. And let's see, and all disks must be stored on a peg. You just can't go take off, you know, you can't just, because that's what these pegs are for. One peg is left for as a holding area. So you can't just say, I'll just hold on to all of them but the one in my hand. So that's the basic rules. So so it turns out for, you know, n disks, it takes 2 to the n minus 1 movements. So for 3 disks, it takes 7 movements to make this thing work. And so you're going to see the recursion on this is so stupid simple, like understanding exactly what we're doing might be difficult, but the code itself is very simple. And then every time I think about it, like I don't even know where to start if I wanted to do this without using recursion. And just how would you know what state you're in, and how would you know, because you just got to pick, well, I got to pick which one of the 3 places to move, and how would I know I'm done? And then all these little, you know, outside conditions and fringe cases and all these things, I have no clue how I would even go about doing it. But the thought process goes, how would I solve this problem? Just think of it abstractly and just say, okay, I have 3 disks on here. What if I could just say, like, don't think about the rules necessarily, think about how you could solve the problem, and just say, well, what if I took 2 disks and I put them here in the middle one, like the top 2, and I should just take them and put them. I could move this guy over to here, and then I could take the 2 disks here and just pop them on top. Like, that's the idea of how to solve this. You say, okay, I have n disks. I want to take from peg 1 to peg 3 using peg 2 as the temporary peg. But what if I was just saying, let's move everyone but the bottom disk to that peg in the middle, and then move the remaining disk over, and then move all the other disks back. That's it. And I swear to God, it is that easy. And you see, like, this is, where's the code? Here it is. Oh, it's a picture file. So I want to move 3 disks, int disks, and I want to move it from A to B, oops, not int, yeah, int A, int B, int C. So what do? I call Hanoi for, I would say I want to move n minus 1 disks. So we're going to say, let's just say A is start, B is the holding peg, and C is the desired end peg. So I'm going to say, start off and say, well, what if I could move, disks minus 1. What if I could move disks minus 1 disks from A to B using C as the holding area? Right, that's kind of like thinking about it here. So if I could say, if I could move from, this is the, oh wait, hold on, to end, make sure I do that, yeah, I have this reversed here. Okay, so I said this is, maybe I should name them, right? Start, hold, and instead of A, B, C. Would it help anybody? We'll find out. So let's forget that. So I say I want to take, so I have the starting peg, I have the holding peg, I have the ending peg, and I want to say, okay, I want to take start number of disks, I want to move them using the holding zone of the C, which is the end. And that's the tricky part here. It's like, because I'm switching things up, right? Like, I wish I had a graphic for this. And I say, because I'm trying to use, in this case, I'm going, the start is still the start. So A is A, but now I'm switching B and C, their purposes. So now the hold area is the end one, and the end one is the hold one. And so that is that. And then I can say, okay, I want to move, and I can say move, just make sure I do from, which is start, and I can say to, and I can say to end. Because that's this one, I know it's weird, it's a print statement. And you go, yes, it's a print statement for the second part, where you take the final disk and you move it over from the start peg to the end peg. And then you take now, starting from the holding peg, because that's where the n minus disks are, n minus 1 disks are, you want to put them in the hold area is actually the start, and then the end is, you know, is the peg that you're looking for. Let me just make sure. Temp, hold, end. Well, if I didn't do it right, then we will find out pretty quickly. Let me just get rid of all this extra nonsense and try it out. So we'll say, let's try Hanoi with three disks going from 1 to 2 and 3 as that area. Let's see. Did I do it right? Uh-oh, where is my arrow? I have arrows. Hold on a second. I have code from, I don't even know where going on here. What in the world? Oh, I forgot about the if statement here also. Sorry about that. Yeah, because like I said, how do I know I'm done, right? So if the number of disks is greater than 0, that's at least one thing, because it's screaming at me that it's recursive on all code paths. And duh, yeah, of course, it's smart enough to know that. Okay, and now this stupid thing. Oh, why is it sorry, it's a void function as well on top of it. Why did I give us pictures? It's so, sorry about that. And so now build one more time. Okay, now it's finally working. Let's see, did I get it to go right? Okay, I think I did. And here we go. So I moved from 1 to 3, then 1 to 2, then 3 to 2. Okay, so that takes care of everything I was thinking about. Again, I'm not explaining the theory behind any of this. It just works. So yes, 1 to 3, 1 to 2, then take, because the 2 is the smallest, or the largest one is now on the, or second to largest. Here, hold on. Let me go back to this slide. There we go. So from 1 to 3, from disk 2 to peg 2. Oh, geez, I can't. From 1 to 2, from 3 to 2, from 1 to 3, from 2 to 1, from 2 to 3, and then 1 to 3. Excellent. We did it right. After me stumbling and stammering and going through all that, it works. So now the cool part is with this, it's like if I want to change it, I can just make it 4. And just say, here's the solution. And again, it comes down to 2 to the n power minus 1 is the number of moves it takes for n disks. So 4 disks takes 15. So everything basically, if you want to think of it, it basically doubles up. So I forget at what point it just becomes unmanageable, because like the print statement is also pretty slow. There we go. Boom, boom, boom. Okay, there. Yep. But every time I do this, if I make this 15, it'll take twice as long as 14 did. And it's always how it works. Everything will be double the time before it. And so here's other code that does the same stuff, their code. And so, oh, they even let a cute little printout. Oh, all the disks are moved. How cute. But anyway, so that's that. So we're almost done here, looks like. Just a couple more slides here. So there's different algorithms for different things. So like with this Tower of Hanoi, we kind of everything just kind of goes through the motion and just kind of works. For the factorial function that in the Fibonacci functions, we just kind of go through the motions and everything works. But my next video and then your homework assignment will have a little bit different when it comes to the thought process behind that kind of stuff. And I'm going to have a video on how to do an n queens problem if I didn't already mention that. So like a lot of times we're going to have problems, like if you think of trying to put queens on a chessboard so that they don't attack each other. And so if I can put 8 queens on a chessboard, then I know that, it's difficult, but there is a way to put them on the chessboard so they don't attack each other because of the way everything works out. But the thing is, if I put 2 of them on the board and they're both attacking each other right off the bat, well, there's no reason to continue forward. There's no reason to do all that extra work when I know right off the bat it's not going to work at all. So I can kind of recurse immediately back and say, nope, that didn't work. Let's go back and try again and put that second queen somewhere else. So again, it's not the same algorithm. It's just basically, it's an exhaustive algorithm that kind of kicks out the bad ideas. So because there's nothing stopping us from just trying and just exhaustively trying every possible combination of 8 queens in 8 places. But that's a ton. That's 4.29 billion different ways that the queens could be set up, because it's 8 times 8 times 8, 8 to the 8th power is, whatever that is, it's 4.4 billion. But that would take a long time. But if I can break it down, I can't remember exactly, but we only look at like 5,000 of those possibilities if we do things a little more smart when it comes to the way we recurse through and use recursion in our algorithms. So just to say, like exhaustive algorithm versus just the general idea, like the general function that just kind of works, there's going to be a little more thought process going in. And so the final slide here, again, the recursion versus iteration, benefits versus disadvantages of both. I say recursion is usually not a lot of code. Say like Tower of Hanoi, my goodness, right? I mean, that's it. That's all there is to solving something that sounds like such a horrendously difficult problem. And so, but the thing is, kind of like with a lot of machine learning stuff, a lot these days, like I don't know how it actually works. I understand, I completely understand the idea, but like at the end of the day when I go, okay, now that I'm trying to move over n minus 1 disks over to here, well, how does that now play into moving n minus 1 of those disks into other places? And it just, and that's where my brain, at least on this problem, my brain just cannot handle that. And if anyone knows of anything intuitive that can explain that, I'd love to hear it. I really would. So I say like, so what are they saying? Shorter, simpler functions, but I like to say it melts your brain. And say a lot of times too, what a lot of this, because I'm using a call stack and I'm pushing and popping a ton of information, it may not be as efficient. And I have to say we could try this if you wanted to kind of experiment and do a recursive versus an iterative, like Fibonacci or something like that. Fibonacci, you know, generally recursion, especially recursion like that, where you're kind of mapping your way through a whole ton of different values, especially if you, like Fibonacci, if you're not finding, like keeping the values, like what is f of 2? Fibonacci of 2, what is Fibonacci of 3? If you're calculating that every single time you're going through and trying to figure out what's the 100th Fibonacci number, you're calculating the same values over and over and over and over and over again. And so, you know, with a little bit of tweaking, you could take an algorithm that takes a long time, days even, down to take seconds. And that's the cool part. That's programming. That's the awesome part of programming, is when you can take something that takes days to do and you can tweak the code around a little bit and you could turn that into something that, you know, takes basically the snap of a finger to solve. So let's see, benefits of iteration. It's more efficient, but again, it's often harder to code. How would you write an iterative version of the Tower of Hanoi? I have no clue. And because I don't even understand it recursively, I don't even want to go into figuring out how to do it iteratively. I've seen the code a few times, and I look at it, and it's about this time every year, I take another look at it and I go, yeah, maybe next time. So that's about it when it comes to this. So you're going to have a homework assignment for those of you who are in my class when it comes to just doing some very simple recursion when it comes to the in-class assignment, and then you'll have a little more fun. At least right now, with the way I teach my class, you will be working on a Sudoku solver. And so it's pretty cool because it's going to exhaustively kind of go through. It's going to kind of do what the Queen's video is going to show too, where you're kind of finding when things aren't wrong, you don't continue on because there's no reason to continue on when the solution doesn't work. But then it just continues, fills in numbers, you know, until it finds that is a solution to the Sudoku puzzle that I have sitting in front of me. It's pretty cool. It really, I mean, and again, it's the computer's doing a lot of that recursive guesswork for us. And it's really cool when it all when it pops and it all fits together, and there's your answer. Pretty cool. All right, so again, swardb@cod.edu if you have any questions for me related to anything that I've done in this video. And thanks for sticking it out. We'll see you next time. I can't get it to stop. It won't let me stop. Oh, bye.